So here's something worth thinking about as you settle in tonight. Right now, wherever you are, you're lying in a world that was fundamentally split in two. Not by politics, not by geography, but by a single moment of understanding. There was the world before humans knew what was inside the atom, and the world after. And the strange thing, the really strange thing, is that the story of how we got from one world to the other doesn't start in a weapons lab or a military bunker. It starts in a quiet room in Paris with a woman puzzling over some photographic plates that had been fogged in a drawer. It starts with pure curiosity. It starts with people who had absolutely no idea where any of this was going. Let's go back there. Let's go back to the very beginning, because the beginning is stranger and more human than most people realize. The year is 1895, and a German physicist named Wilhelm Röntgen is working late one evening in his laboratory at the University of Würzburg. He's experimenting with cathode rays. Basically, he's running electrical current through a glass tube from which most of the air has been pumped out, watching what happens. Scientists all over Europe were doing this kind of thing at the time. It was one of the hot research areas of the day, no pun intended. But on this particular November evening, Röntgen notices something that stops him cold. A fluorescent screen sitting on a bench nearby, a screen that has nothing to do with his experiment, is glowing. It's responding to something. Some kind of invisible ray is coming out of his apparatus, passing through the air, passing through solid objects, and hitting that screen. He holds up a piece of cardboard between the tube and the screen. The screen still glows. He tries a book, still glowing. He tries a thin sheet of metal. The glow dims, but doesn't stop. And this is the moment that changes everything. He puts his hand between the tube and the screen, and he sees the shadow of his own bones, his own skeleton, projected in real time, through his living flesh. He doesn't tell anyone for weeks. He practically moves into his laboratory, sleeping there, eating there, running experiment after experiment. His wife later said he was like a man possessed. When he finally shows her what he's found, he takes an image of her hand. You've probably seen it, the bones of her fingers with her wedding ring floating around one of them. And she reportedly says, "I have seen my death," which is dramatic, sure, but also kind of understandable. Nobody had ever seen inside a living human body before. Not like that. Röntgen calls them X-rays, the X standing for unknown, and the discovery electrifies the entire scientific world almost overnight. Within weeks, laboratories everywhere are reproducing his results. Doctors immediately see the medical applications. But here's what matters for our story. Röntgen's discovery cracks open a door. It tells the physics community that there are invisible emanations, unseen forms of energy, radiating from matter in ways nobody had predicted. And that realization sends dozens of brilliant minds racing to figure out what else might be hiding in the invisible world. One of those minds belongs to Henri Becquerel, a French physicist in Paris. Becquerel comes from a family of scientists. His father and grandfather both studied phosphorescence, which is the phenomenon where certain materials absorb light and then re-emit it, glowing in the dark for a while after you take the light away. When Becquerel hears about X-rays, he has a reasonable hypothesis. Maybe phosphorescent materials are emitting X-rays along with their visible glow. So in early 1896, he sets up an experiment. He takes crystals of a uranium salt, potassium uranyl sulfate, a substance known to phosphoresce, and places them on top of photographic plates wrapped in thick black paper. The idea is simple. He'll expose the crystals to sunlight to get them glowing, and if they're also emitting X-rays, those rays should pass through the black paper and fog the photographic plate underneath. He runs the experiment, develops the plates, and sure enough, there are shadowy images on them. He thinks he's confirmed his hypothesis. But then Paris does what Paris does. The weather turns cloudy. For several days, there's no sunlight. Becquerel has prepared another set of plates with uranium crystals sitting on top of them, but he can't run the experiment because there's no sun to activate the phosphorescence. He sticks the whole setup in a drawer and waits. When he finally pulls the plates out and develops them, almost as an afterthought, expecting to see maybe a faint image at best, the fogging on the plates is just as strong as before. Maybe stronger. The uranium crystals had been sitting in total darkness inside a closed drawer, and they were still emitting something. Something that had nothing to do with phosphorescence, nothing to do with sunlight, nothing to do with any external energy source at all. The uranium itself was spontaneously giving off invisible rays, all on its own, all the time. Think about what that means. This isn't a material responding to energy being put into it. This is a material just radiating, continuously, from within. Where is that energy coming from? What is the source? In 1896, nobody has the faintest idea. The atom, as far as most physicists are concerned, is still the fundamental, indivisible building block of matter. The word atom literally comes from the Greek atomos, meaning uncuttable. And yet here's uranium, apparently pouring out energy from somewhere deep inside itself, with no obvious mechanism and no apparent limit. Becquerel publishes his findings, and the scientific community is intrigued, but not quite sure what to make of it. It's a curiosity, an oddity. But there's a young Polish-born scientist living in Paris who decides this oddity is exactly the thing she wants to build her doctoral research around. Her name is Maria Skłodowska, though you know her by her married name, Marie Curie. And here's where the human story gets really compelling, because Marie Curie's path to this moment is anything but easy. She grew up in Warsaw under Russian occupation, at a time when Poles, and especially Polish women, were systematically denied access to higher education. She attended an illegal underground university. She worked as a governess for years to save money. She finally made it to Paris and the Sorbonne in 1891 at the age of 23, often studying in an unheated garret, so cold that the water in her wash basin would freeze overnight. She survived on bread and chocolate and sheer, relentless determination. By the time she encounters Becquerel's uranium rays in 1897, she's married Pierre Curie, a brilliant physicist in his own right, and she's looking for a dissertation topic that's genuinely new, genuinely unexplored. Becquerel's rays fit perfectly. Almost nobody else is working on them. What Marie Curie does next is methodical and quietly revolutionary. She doesn't just study uranium. She systematically tests every element she can get her hands on, checking whether any of them emit these mysterious rays. She uses an ingenious device, an electrometer designed by Pierre and his brother, that can detect extremely faint electrical charges in the air. Because whatever these rays are, they ionize the air around them. They knock electrons loose from air molecules, and that ionization can be measured as a tiny electrical current. So she has a way to quantify the rays, to measure their intensity precisely, and she tests element after element after element. She finds that thorium also emits rays, just like uranium. And then she makes a discovery that changes the direction of everything. She tests a mineral called pitchblende, which is a uranium ore, and finds that it's significantly more radioactive, a term she coins herself, by the way, radioactivity, than pure uranium alone should account for. The math doesn't work. Pitchblende is more active than the uranium in it can explain, which means there must be something else in that ore, some unknown element, something never before identified, that's even more intensely radioactive than uranium. So she and Pierre set about finding it. And this is where the work becomes genuinely grueling. They're processing tons, literally tons, of pitchblende ore in a leaky shed that used to be a medical school dissecting room. They're grinding, dissolving, filtering, precipitating, boiling down enormous quantities of material to isolate tiny, tiny traces of new elements. The work is physically exhausting, chemically dangerous, and incredibly tedious. Marie later described it as the hardest period of her life, and this is a woman whose life was not short on hardship. But they find what they're looking for. In 1898, they announced the discovery of not one, but two new elements. The first they name polonium, after Marie's beloved homeland. The second they name radium. And radium, it turns out, is astonishingly, almost unbelievably radioactive. A pure radium salt glows in the dark with an eerie blue-white light. It's warm to the touch from the energy it's constantly releasing. It can burn skin. A tiny speck of it fogs photographic plates from across the room. It is pouring out energy at a rate that, by the physics of the day, seems flatly impossible. Where is all that energy coming from? How can a lump of matter just sit there on a table and radiate heat and light indefinitely? It seems to violate the conservation of energy, one of the most fundamental laws of physics. Something is deeply, fundamentally wrong with the way scientists understand the atom. And this is the crack in the foundation. This is the loose thread that, when pulled, will eventually unravel everything. Because the question Becquerel stumbled into, and the Curies chased with such tenacity, where does the energy come from? Turns out to have an answer so profound that it will reshape civilization. The energy comes from inside the atom. The atom is not indivisible. It has an interior structure, and within that structure, there are forces of almost inconceivable magnitude locked away. But we're getting ahead of ourselves. In 1898, nobody knows any of that yet. The Curies know they've found something extraordinary, but the theoretical framework to explain it doesn't exist. That framework is about to be built, though, piece by piece, by a remarkable cast of characters scattered across Europe. And one of the first major pieces comes from a New Zealander working in a basement laboratory in Cambridge, England. His name is Ernest Rutherford, and he's one of those figures in science who's so important that it's almost hard to believe he was a single person. Rutherford is big, loud, brash, and brilliant, the opposite of the quiet, meticulous Curies in temperament, but every bit their equal in insight. He grew up on a farm in rural New Zealand, the son of a flax miller, and he won a scholarship to Cambridge that quite literally changed the course of human history. The story goes that when the telegram arrived, telling him he'd won the scholarship, he was digging potatoes in his mother's garden. He threw down the spade and said, "That's the last potato I'll ever dig." And he was right. At Cambridge, Rutherford begins working under J.J. Thomson, who, in 1897, has just made his own world-shaking discovery, the electron. Thomson shows that cathode rays are actually streams of tiny, negatively charged particles, far smaller than any atom, and that these particles can be pulled out of atoms of every element, which means the atom has parts. It contains these little negative charges, these electrons. Thomson proposes a model of the atom, sometimes called the plum pudding model, where the atom is a sphere of diffuse positive charge with electrons embedded in it, like raisins in a pudding. It's a reasonable first guess. It explains the electrical neutrality of atoms, since the positive and negative charges balance out. But it's wrong, and it's Rutherford who will prove it's wrong in one of the most famous experiments in all of physics. But that comes a little later. First, Rutherford turns his attention to Becquerel's rays, the mysterious radiation coming out of uranium and thorium and radium, and he discovers something crucial. There isn't just one kind of radiation. There are at least two. He calls them alpha rays and beta rays, simply because he doesn't know what they are yet, so he names them after the first two letters of the Greek alphabet. Alpha rays, he finds, are heavy and positively charged. They can be stopped by a sheet of paper. Beta rays are lighter and negatively charged. They can penetrate much further through thin metal, but they're stopped by a few millimeters of aluminum. Later, a third type is discovered and named gamma rays. These are incredibly penetrating, able to pass through thick lead shielding, and they carry no charge at all. What's happening, though nobody fully understands it yet, is that atoms of certain elements are spontaneously breaking apart. They're ejecting pieces of themselves. Alpha particles turn out to be the nuclei of helium atoms, beta particles turn out to be high-speed electrons, and gamma rays turn out to be a form of electromagnetic radiation even more energetic than X-rays. The atom isn't just sitting there passively. In certain heavy elements, it's actively disintegrating, transforming itself into a different element in the process. Uranium decays into thorium. Thorium decays into something else. Each step releases energy. This is radioactive decay, and it's the first hint that the atom contains a staggering amount of locked-up energy. Rutherford and a chemist named Frederick Soddy work out the theory of radioactive transmutation around 1902, and when they realize what they're saying, that one element is spontaneously changing into another element, Soddy reportedly exclaims, "Rutherford, this is transmutation." And Rutherford, ever practical, ever aware that the scientific establishment might not take kindly to language that sounds like medieval alchemy, shoots back, "For God's sake, Soddy, don't call it transmutation. They'll have our heads off as alchemists." But that's exactly what it is. The ancient dream of the alchemists, turning one element into another, is actually happening, not in a crucible over a fire, but spontaneously, inside the atoms themselves, all around us, all the time. And now a quiet question starts forming in the minds of a few physicists, a question that won't be answered for decades, but that already carries an enormous weight. If atoms can release energy when they decay on their own, slowly, one by one, is there a way to make them release that energy all at once? Is there a way to unlock it deliberately, on command, in bulk? Because if you could do that, the amount of energy available would be almost unimaginable. Rutherford himself does a rough calculation. He figures that a single pound of radium, if you could release all of its energy at once, would contain enough to lift 1,000,000 tons a mile into the air. A pound of material. 1,000,000 tons. A mile. Those numbers don't even sound real, and yet the math checks out. The energy locked inside the atom is orders of magnitude greater than anything chemistry can offer, greater than dynamite, greater than any fuel anyone has ever burned. The question is whether nature will let you get at it. And for a while, most physicists, including Rutherford himself, think the answer is probably no. The energy is there, sure, but it leaks out so slowly during natural radioactive decay that it seems like there's no practical way to speed it up. It's like knowing there's a vast underground lake beneath your feet, but having no drill, no pump, no way to reach it. You can watch the occasional drop seep through the rock, but you can't turn on the tap. That's roughly where things stand in the early 1900s. The energy is real. The mechanism to release it in useful quantities doesn't exist, and most serious scientists assume it never will. But here's the thing. While that big question simmers in the background, Rutherford keeps doing what Rutherford does best, which is designing clever experiments. And in 1909, he sets up one of the most important experiments in the history of physics. He's at the University of Manchester now, and he has two younger researchers working with him, Hans Geiger, a German physicist, and Ernest Marsden, an undergraduate who's barely 20 years old. Rutherford asks them to do something that sounds almost trivially simple. He wants them to fire alpha particles, those little chunks of helium nuclei that get spit out during radioactive decay, at a thin sheet of gold foil and see what happens. See where the alpha particles end up after they pass through. Now, the expectation is straightforward. At this point, the reigning model of the atom is still J.J. Thomson's plum pudding model, the one where the atom is a diffuse blob of positive charge with electrons scattered through it like raisins in a pudding. If that model is right, then alpha particles, which are relatively heavy and fast-moving, should punch straight through the gold foil with only slight deflections. Maybe they'd get nudged a tiny bit off course, the way a bullet might wobble slightly passing through a cloud of cotton candy. But they should all come out the other side, more or less going the same direction they went in. And that's mostly what happens. Most of the alpha particles zip right through. Geiger and Marsden sit in a darkened room, watching a zinc sulfide screen for tiny flashes of light, each flash marking where an alpha particle strikes, hour after hour in the dark, counting flashes. Tedious, painstaking work. But then they notice something strange. A few of the alpha particles, a very small fraction, are bouncing back. Not just deflecting slightly. Bouncing back toward the source, as if they've hit something solid inside the atom and ricocheted. Some are deflected at angles greater than 90 degrees. When Rutherford hears about this, he's stunned. He later describes his reaction with one of the most quoted lines in physics. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Think about that image. You're shooting cannonballs at tissue paper, and occasionally, one comes flying back at your face. That's not supposed to happen. That can't happen, unless there's something very small, very dense, and very hard hiding inside that tissue paper. And from this, Rutherford works out a completely new model of the atom. He publishes it in 1911. The atom, he says, is mostly empty space. Almost all of its mass is concentrated in a tiny, dense core at the center, what he calls the nucleus. The electrons orbit far out from this nucleus, like planets orbiting a distant sun, with vast emptiness in between. The reason most alpha particles pass straight through the gold foil is that they're sailing through that empty space, never coming near the nucleus. But the rare alpha particle that happens to fly directly toward a nucleus, this tiny, incredibly dense target, gets deflected violently, sometimes bouncing straight back. This is a revolution. The plum pudding model is dead. The atom has structure. It has a center. And that center is where essentially all the mass lives, packed into a space that's something like 100,000 times smaller than the atom itself. If the atom were the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. Everything else, all that space where the seats are, where the field is, where the hot dog vendors walk around, is empty. The atom is almost entirely nothing. Now, this raises a beautiful and slightly unsettling question. If the nucleus is positively charged and the electrons are negatively charged and opposite charges attract, why don't the electrons just spiral inward and crash into the nucleus? Classical physics says they should. An orbiting charged particle should radiate energy, lose speed, and collapse into the center in a fraction of a second. Every atom in the universe should be unstable. And yet, here we are, made of atoms, very much not collapsing. Something is wrong with the classical picture. This is where a young Danish physicist named Niels Bohr enters the story. And honestly, you could argue that Bohr is one of the most important figures in this entire narrative, not just for what he discovers, but for the role he'll play decades later when the bomb becomes real. But we'll get to that. For now, in 1913, Bohr is a young man who's recently spent time in Manchester with Rutherford, and he proposes a radical fix. He says electrons don't orbit the nucleus in just any path they like. They can only exist in specific fixed orbits, discrete energy levels. An electron can jump from one level to another by absorbing or emitting a precise amount of energy, but it can't exist in between. It's as if you're climbing a staircase and you can stand on any step, but you can never stand between steps. Your foot is either on one step or another, never halfway. This is the birth of quantum mechanics applied to the atom. And it's strange, and it doesn't make intuitive sense. And Bohr knows that. But it works. It explains the specific wavelengths of light that hydrogen emits. It explains why atoms are stable. It explains things that classical physics simply cannot. And it introduces this idea that, at the atomic scale, the rules are different. Energy comes in packets. Certain values are allowed and others are forbidden. Nature, at its smallest scale, is not smooth and continuous. It's granular, jumpy, quantized. Over the next 2 decades, from roughly 1913 to the early 1930s, quantum mechanics gets built out by an extraordinary generation of physicists. Bohr in Copenhagen, Werner Heisenberg, who develops matrix mechanics and the famous uncertainty principle, the idea that you can't simultaneously know both the exact position and exact momentum of a particle. Erwin Schrödinger, who formulates his wave equation, giving a mathematical framework for how quantum particles behave. Max Born, who interprets Schrödinger's waves as probability distributions. Paul Dirac, who merges quantum mechanics with special relativity. Wolfgang Pauli, who establishes the exclusion principle, the rule that no 2 electrons in an atom can occupy the same quantum state, which is ultimately why the periodic table looks the way it does, why chemistry works the way it works, why matter has the structure it has. This is an astonishing period. These physicists are mostly young, many of them in their 20s, and they're rewriting the fundamental rules of reality. They argue with each other constantly. Bohr and Einstein have legendary debates about whether quantum mechanics is truly random or whether there's some deeper, hidden order beneath it. Einstein famously protests, "God does not play dice with the universe." And Bohr, in one of the great comebacks in scientific history, reportedly replies, "Einstein, stop telling God what to do." But here's what matters for our story. All of this theoretical machinery, quantum mechanics, the understanding of atomic structure, the mathematics of how particles behave inside nuclei, is building the intellectual foundation for what comes next. Because you can't understand nuclear fission without understanding the nucleus, and you can't understand the nucleus without quantum mechanics. These are the tools that will eventually make the bomb thinkable. Meanwhile, experimentalists are making their own progress. In 1919, Rutherford achieves something remarkable. He becomes the first person to deliberately transmute one element into another, not by watching natural radioactive decay happen passively, but by actively forcing it. He bombards nitrogen gas with alpha particles and detects that some of the nitrogen atoms are being converted into oxygen, with protons being knocked loose in the process. He's literally changing one element into another by hitting atoms hard enough to rearrange their parts. The alchemist's dream, achieved not with philosophers' stones, but with subatomic projectiles. And in 1920, Rutherford makes a prediction. He suggests that inside the nucleus, alongside the protons, there might be another particle, one with roughly the same mass as a proton, but no electric charge, a neutral particle. He even suggests a name for it. He calls it the neutron. It takes 12 years for someone to find it, but in 1932, James Chadwick, another one of Rutherford's protégés, a man who'd spent 4 years in a German internment camp during World War I, doing physics experiments with improvised equipment made from toothpaste tubes and tinfoil, Chadwick finally identifies the neutron experimentally. And this discovery changes everything. Here's why the neutron matters so much. Before the neutron, if you wanted to probe the inside of an atom or smash into a nucleus, you had to use charged particles. Alpha particles or protons. But charged particles get repelled by the positive charge of the nucleus. It's like trying to push two magnets together with the same poles facing each other. You have to overcome that electromagnetic repulsion, which means you need a lot of energy. But the neutron has no charge. It's electrically neutral. It can sail right past the electromagnetic barrier and waltz straight into the nucleus without being repelled. It's like having a key that bypasses the lock entirely. And this is where the story starts accelerating, because now physicists have a new tool, a neutral bullet they can fire at atomic nuclei, and they start using it immediately. In Rome, a young Italian physicist named Enrico Fermi begins systematically bombarding every element he can get his hands on with neutrons, working his way through the periodic table. Fermi is brilliant, practical, and fast. His team in Rome, sometimes called the Boys of Via Panisperna, after the street where their lab is located, discovers something unexpected. When they slow the neutrons down, when they pass them through paraffin or water before letting them hit the target, the neutrons become more effective at triggering nuclear reactions. This is counterintuitive. You'd think faster, more energetic neutrons would be better at smashing into things, but slow neutrons spend more time near the nucleus, giving them a better chance of being captured. It's like the difference between throwing a ball past someone's glove and lobbing it gently so they can catch it. Fermi's team works through element after element, and when they get to uranium, element 92, the heaviest naturally occurring element, they bombard it with neutrons and get results they can't quite explain. They detect radioactive products that don't match any known element near uranium on the periodic table. Fermi cautiously suggests they might have created new elements heavier than uranium. Transuranic elements, elements 93 and 94, things that don't exist in nature. It's a reasonable guess. The scientific community largely accepts it. Fermi even receives the Nobel Prize in 1938, partly for this work. But there's a problem. A chemist in Berlin named Ida Noddack publishes a paper in 1934 suggesting something far more radical. Maybe, she says, the uranium nucleus isn't absorbing the neutron and getting bigger. Maybe it's breaking apart. Maybe it's splitting into two lighter elements. Almost nobody takes her seriously. The idea seems absurd. How could a tiny neutron shatter a massive uranium nucleus into two roughly equal pieces? It would be like throwing a pebble at a boulder and having the boulder crack in half. The physics community essentially ignores her suggestion. But Nobel is right. And it will take 4 more years, and a team in Berlin working over Christmas in 1938 to prove it. The people who finally crack the puzzle are Otto Hahn and Fritz Strassmann, 2 chemists who've been carefully repeating and refining Fermi's uranium experiments. And what they find in their lab in December of that year is so strange, so unexpected, that Hahn barely trusts his own results. He writes a letter to his longtime collaborator, a physicist named Lisa Meitner, who by this point has been forced to flee Germany because she's of Jewish heritage. She's in Sweden now, spending Christmas with her nephew Otto Frisch, who's also a physicist. And when Meitner reads Hahn's letter describing what he's found in his laboratory, barium, of all things, showing up in the residue of bombarded uranium, barium with an atomic number of 56, barely more than half of uranium's 92. She and Frisch go for a walk in the snowy Swedish woods, and they start working through the physics on scraps of paper, and they realize what's happening. The uranium nucleus is splitting, not chipping off a piece, not absorbing and growing, splitting. The nucleus of uranium, this massive thing with 92 protons and a whole crowd of neutrons packed together, is dividing itself into 2 smaller nuclei, and barium is one of the products. Meitner knows her physics deeply enough to see what this means almost immediately. She thinks about the nucleus the way Bohr had been describing it, not as a rigid ball, but more like a liquid drop, held together by nuclear forces, but always wobbling, always on the edge of instability. And when a neutron slips into a uranium nucleus, it adds just enough energy to set that drop wobbling more violently, elongating, stretching, until the electrical repulsion between all those positively charged protons in the 2 bulging ends overcomes the nuclear force trying to hold everything together, and the drop pinches in the middle and tears itself in 2. Frisch later says they sat down on a tree trunk in the snow to work out the energy. And this is where it gets breathtaking. Meitner pulls out the key numbers from memory. She knows that the mass of a uranium nucleus is slightly more than the combined masses of the 2 fragments it would break into. That difference in mass, it's tiny, less than 1/5 of a proton's mass. But Einstein's equation, that famous E equals mc squared, tells you that even a tiny amount of mass, when converted to energy, produces an enormous result. She calculates roughly 200 million electron volts released in a single fission event. 200 million. For comparison, a chemical reaction, burning coal, detonating TNT, releases maybe 1 or 2 electron volts per atom. So a single uranium atom splitting releases something like 100 million times more energy than a single atom undergoing a chemical reaction. Let that sink in for a moment. 1 atom, 1 event, 100 million times more energy than burning. Frisch rushes back to Copenhagen and tells Bohr, who's about to leave for the United States. And Bohr's reaction is legendary. He slaps his forehead and says something like, "Oh, what fools we've been. We should have seen this before." Because in hindsight, all the clues were there. Nobel had even said it outright 4 years earlier. But the idea was so radical, so outside the framework everyone was working in, that it took the undeniable chemical evidence, barium sitting there in the residue, impossible to explain any other way, to force the realization. Frisch is the one who coins the term fission, borrowing it from biology, where cells undergo fission when they divide. He and Meitner published their theoretical explanation in February 1939 in the journal Nature. Hahn and Strassmann published the chemical evidence separately. And here's something that still bothers historians. When the Nobel Prize is awarded for this discovery in 1944, it goes to Hahn alone. Meitner is excluded. Strassmann is excluded. The reasons are complicated. Wartime politics, the Nobel Committee's biases, the way credit gets assigned when chemistry and physics overlap. But many scientists then and now consider it one of the great injustices in the history of the Nobel Prize. Meitner provided the physical explanation that made sense of Hahn's chemical results. Without her insight on that walk in the snow, the barium would have remained a puzzling anomaly. She lived to be 89, was nominated for the Nobel Prize multiple times, and never received it. Element 109, Meitnerium, is named in her honor, which is a kind of recognition, but it came long after she died. Now, Bohr arrives in the United States in January 1939, and the news of fission spreads through the American physics community like a shockwave. Within weeks, labs across the country are confirming the result. It's not hard to do. You bombard uranium with neutrons and look for the fission fragments. Enrico Fermi, who's now at Columbia University in New York, having left Italy partly because of his wife Laura's Jewish heritage and the rising fascist threat, immediately starts thinking about what comes next. And what comes next is the question that changes everything. Here's the thing about fission that makes it more than just a spectacular laboratory curiosity. When a uranium nucleus splits, it doesn't just release energy, it also releases neutrons, typically 2 or 3 of them, flying out from the fission fragments at high speed. And each of those neutrons can, in principle, strike another uranium nucleus and cause it to split, releasing more energy and more neutrons, which cause more fissions, which release more neutrons. You can see where this is going. It's a chain reaction. 1 fission causes 2, 2 cause 4, 4 cause 8. And within a tiny fraction of a second, you have an astronomical number of fissions happening almost simultaneously, each one releasing 200 million electron volts. The total energy released would be staggering, unimaginable, enough to level a city. This realization doesn't come to just one person. It comes to many physicists almost simultaneously in early 1939. Bohr discusses it. Fermi discusses it. Leo Szilard, and here's a name you should know. Szilard had actually conceived of the nuclear chain reaction idea back in 1933, years before fission was even discovered. He was a Hungarian physicist living in London, and he'd read a novel by H.G. Wells called The World Set Free, published in 1914, which imagined atomic bombs. Szilard was crossing a street in London. The story goes it was the intersection at Southampton Row, when the idea of a neutron chain reaction hit him. If you could find an element that, when hit by a neutron, released 2 neutrons, you'd have an exponentially growing reaction. He even filed a patent on the concept in 1934 and assigned it to the British Admiralty to keep it secret. But at the time, he didn't know which element might work. Now, with the discovery of fission, he knows. It's uranium. Szilard is terrified. He's a Jewish refugee from Hungary who understands exactly what the rise of Nazism means, and he immediately grasps the military implications. If a chain reaction in uranium is possible, then an atomic bomb is possible. And if it's possible, then Germany, which has some of the best physicists in the world, which is where fission was discovered, which has access to uranium from Czechoslovakia, might build one first. This fear drives everything that happens next. But before anyone can build a bomb, There are enormous practical problems to solve, and the first one is this. Not all uranium is created equal. Natural uranium is a mixture of two main isotopes. About 99.3% of it is uranium-238, and only about 0.7% is uranium-235. They're chemically identical. Same number of protons, same electron configuration, same chemical behavior. The only difference is 3 extra neutrons in the heavier isotope. But that difference is everything. Because it turns out that uranium-235 is the isotope that fissions readily when struck by a slow neutron. Uranium-238 tends to just absorb the neutron without splitting, at least at low energies. So if you want a chain reaction, you need to either work with natural uranium in a very carefully designed system, or you need to separate out the rare uranium-235 from the abundant uranium-238. And separating two isotopes of the same element is nightmarishly difficult. You can't use chemistry, because isotopes are chemically identical. You have to exploit the tiny difference in mass, 3 neutrons worth out of 235 or 238. That's a mass difference of barely 1%. Imagine trying to sort tennis balls that are all the same size, same color, same texture, but some weigh 1% more than others. Now imagine you need to sort billions of them, and you need the lighter ones with very high purity. That's essentially the isotope separation problem, and it will become one of the most expensive and technically demanding engineering challenges in human history. But we're getting ahead of ourselves. In the spring of 1939, the immediate question is simpler. Can a chain reaction actually be sustained? Because there are reasons it might not work. Neutrons released by fission are fast. They're moving at enormous speeds. And fast neutrons aren't very efficient at causing fission in uranium-235. They tend to zip right past nuclei without interacting. Remember Fermi's discovery about slow neutrons being more effective? That same principle applies here. If you could slow the neutrons down, moderate them, they'd be much more likely to cause additional fissions. But if you slow them down in the presence of uranium-238, that isotope might just absorb them before they can reach a uranium-235 nucleus. So you need a moderator, a material that slows neutrons without absorbing too many of them. Fermi, now at Columbia, starts working on this problem with Szilard. And Szilard, who is brilliant but also incredibly difficult to work with. He's abrasive, impatient, and has a habit of telling other physicists what to do. Szilard proposes using graphite as a moderator. Carbon nuclei are light enough to slow down neutrons efficiently through collisions, and carbon doesn't absorb neutrons very readily. It's also cheap and available in large quantities. The alternative is heavy water made with deuterium instead of ordinary hydrogen, which is an even better moderator, but far harder to obtain. So Fermi and Szilard begin a series of experiments at Columbia, stacking blocks of graphite and embedding lumps of uranium oxide in them, trying to measure whether neutrons are multiplying or dying out. They're looking for a number, a critical number that will determine whether a chain reaction is possible. They call it K, the multiplication factor. If K is greater than 1, it means each generation of fissions produces more neutrons than the last, and the reaction will grow. If K is less than 1, the reaction fizzles out, and in those early experiments at Columbia, K is stubbornly less than 1, Close, tantalizingly close, but not quite there. The graphite isn't pure enough. Commercial graphite contains traces of boron, which is a voracious neutron absorber. The uranium oxide isn't dense enough, isn't arranged optimally. There are losses at every stage. Meanwhile, the political situation is accelerating. In August 1939, Szilard drafts a letter to President Franklin Roosevelt, warning him about the possibility of an atomic bomb and urging the United States to begin its own research program. He convinces Albert Einstein, the most famous scientist in the world, to sign it. Einstein's involvement is ironic in a way, because Einstein's own contribution to the physics of fission is limited to that foundational equation, E equals mc squared, which he published in 1905 as part of special relativity. Einstein isn't a nuclear physicist, but his name carries weight that no other scientist's does. The letter is delivered to Roosevelt in October 1939, a month after Germany invades Poland and World War II begins in Europe. Roosevelt's response is measured but significant. He establishes the Advisory Committee on Uranium, which holds its first meeting on October 21, 1939. The committee includes military representatives and scientists, and its early work is cautious, underfunded, and slow. The initial grant for uranium research is $6,000, barely enough to buy the graphite Fermi needs. Compare that to what's coming. The Manhattan Project will eventually spend nearly $2 billion 1940s dollars, equivalent to roughly $30 billion today. But in late 1939, nobody yet knows whether an atomic bomb is even physically possible. The chain reaction hasn't been demonstrated. The isotope separation problem looks almost insurmountable. And plenty of respected physicists think the whole idea is a fantasy. What changes the pace? What transforms this from a modest research program into the largest engineering project in human history is a combination of scientific progress and mounting fear. And the scientific progress comes from an unexpected direction, from two refugee physicists working in England in the spring of 1940, who sit down and do a calculation that changes everything. Their names are Otto Frisch, yes, the same Frisch who helped his aunt, Lise Meitner, work out the physics of fission over Christmas 1938, and Rudolf Peierls, a German-born theoretical physicist who had settled in Birmingham, England. Both are refugees from Nazi persecution. Both are technically enemy aliens in wartime Britain, which means they're excluded from the official war research being done on things like radar. So they have time on their hands, and they have a question that nobody else seems to have properly answered. Just how much uranium-235 would you actually need to make a bomb? See, up to this point, most physicists who'd thought about the problem had been vaguely pessimistic. They assumed you'd need tons of the stuff, literally tons of pure U-235. And since U-235 makes up only about 0.7% of natural uranium, separating tons of it seemed so absurdly impractical that the whole idea felt academic. Even Niels Bohr, who understood fission as well as anyone alive, had reportedly said that building an atomic bomb would require turning the entire country into a factory. And he may have meant it partly as reassurance, a way of saying, don't worry, this can't actually happen. But Frisch and Peierls sit down in February or March of 1940, and they do the calculation properly, using the latest estimates for the fission cross-section of U-235. That is, the probability that a fast neutron will actually trigger a fission event when it hits a U-235 nucleus. And what they find is stunning. You don't need tons, you need kilograms. Their estimate is roughly 1 pound, maybe a few pounds. The actual critical mass turns out to be larger than their initial estimate, somewhere around 50 kilograms for a bare sphere of U-235, though you can reduce it significantly with a neutron reflector. But even the corrected number is still measured in kilograms, not tons, and that changes the entire calculation. Because kilograms of U-235, while extraordinarily difficult to produce, are not impossible to produce. It's an engineering problem, not a physical impossibility. Frisch and Peierls write up their findings in a brief document, just a few pages, that becomes known as the Frisch-Peierls Memorandum, and it's remarkable not just for the physics, but for the clarity and the moral seriousness with which they lay out the implications. They describe what such a bomb would do. The blast, the heat, the radioactive contamination that would make the area dangerous for a long time afterward. They note that such a weapon would be essentially indiscriminate, killing civilians and soldiers alike. And they warn that Germany, which has access to Czechoslovakian uranium mines and some of the best nuclear physicists in the world, might be working on exactly the same thing. The memo is delivered to Mark Oliphant, an Australian physicist at the University of Birmingham, who passes it up the chain to Henry Tizard, one of Britain's most influential scientific advisors. The British response is dramatically different from the American one. Where Roosevelt's Advisory Committee on Uranium moved cautiously and spent $6,000, the British government quickly establishes a secret committee codenamed MAUD, a name that comes from a garbled telegram and has no particular meaning, which is actually useful for secrecy. The MAUD committee brings together some of Britain's best physicists, and over the next year and a half, they produce a detailed technical report concluding that an atomic bomb is feasible, that it could be built in time to affect the outcome of the war, and that work should begin immediately. The Mayhew report, finalized in July 1941, is one of the most consequential scientific documents of the 20th century, because it's what finally convinces the Americans to get serious. And here's the thing. The Americans needed convincing. Through 1940 and into 1941, the uranium research program in the United States is still moving slowly. There are bureaucratic tangles, funding is limited, and there's genuine scientific skepticism about whether a bomb is practical. Fermi and Szilard are still working on their graphite uranium lattice experiments at Columbia, trying to achieve a self-sustaining chain reaction. And they're making progress, but they're not there yet. The multiplication factor, the number of neutrons produced per generation compared to the number lost, keeps coming up short. They need it above 1, and they're getting values like 0.87. Close, but close doesn't count when you're trying to start a chain reaction. The problem is partly the purity of their materials. Commercial graphite contains trace amounts of boron, and boron is a voracious neutron absorber. Even a few parts per million can kill your chain reaction. So Szilard, with his characteristic combination of brilliance and persistence, starts working with graphite manufacturers to produce ultra-pure material. But the real acceleration comes after the MAUD report reaches America. Mark Oliphant actually flies to the United States in August 1941, partly because he's frustrated that the Americans don't seem to be reading the reports the British are sending. He meets with various American scientists and officials, essentially banging on doors and saying, "This is real, this is urgent, you need to act," and it works. Vannevar Bush, who heads the Office of Scientific Research and Development, takes the findings to Roosevelt. On October 9, 1941, 2 months before Pearl Harbor. Roosevelt approves a full-scale effort to develop an atomic bomb. The project is reorganized, properly funded, and placed under the authority of the Army Corps of Engineers. It will eventually be codenamed the Manhattan Engineer District, and then simply the Manhattan Project. Now let's pause here and think about what this project actually requires, because the engineering challenges are almost incomprehensible in their scale and complexity. You need to solve at least 3 enormous problems simultaneously. First, you need to produce enough fissile material, either uranium-235 or plutonium-239, which we haven't talked about yet, to build a bomb. Second, you need to design a weapon that will actually work, meaning you need to figure out how to assemble a supercritical mass fast enough that the chain reaction runs to completion before the thing blows itself apart. And third, you need to do all of this in secret during a world war on a timeline measured in months rather than decades. Let's talk about plutonium for a moment, because it enters the story here, and it's absolutely crucial. In 1940, a team at the University of California, Berkeley, led by Glenn Seaborg, Edwin McMillan, and others, discovers element 94, plutonium. They produce it by bombarding uranium-238 with neutrons in a cyclotron. When U-238 absorbs a neutron, it becomes U-239, which is unstable and undergoes 2 successive beta decays, each one converting a neutron into a proton, transforming first into neptunium-239 and then into plutonium-239. And here's what's really clever about this. What makes it so important? Plutonium-239, like uranium-235, is fissile. It can sustain a chain reaction. It can be used in a bomb. But unlike U-235, which you have to painstakingly separate from the much more abundant U-238, 2 isotopes of the same element with nearly identical chemical properties, plutonium is a different element entirely. That means you can separate it from uranium using chemistry, which is dramatically easier than isotope separation. You still have to produce it first, which requires a nuclear reactor. But once you have a working reactor, you can breed plutonium in meaningful quantities. This is why the chain reaction matters so much, not just as a scientific milestone, but as an industrial necessity. You need a reactor to make plutonium. And to build a reactor, you need to solve the problems Fermi and Szilard have been wrestling with at Columbia. Pure enough graphite, pure enough uranium, the right geometry, the right lattice spacing. By 1942, the work has moved to the University of Chicago, where Fermi is assembling what he calls a pile, layers of uranium metal and uranium oxide arranged in a lattice within blocks of ultra-pure graphite, stacked up in a squash court under the west stands of Stagg Field, the university's abandoned football stadium. Think about that for a second. The world's first nuclear reactor is being built under the bleachers of a football field in the middle of a major American city. There are no containment structures, no radiation shielding to speak of, no emergency cooling systems. If something goes wrong, if the reaction runs away, the consequences could be catastrophic. Fermi is confident in his calculations, and his confidence turns out to be justified, but the risks are real and everyone involved knows it. The pile grows layer by layer through the fall of 1942. Fermi's team takes careful measurements at each stage, tracking the multiplication factor as it creeps upward. They use cadmium control rods, cadmium being another excellent neutron absorber, that can be inserted into the pile to keep the reaction in check. The idea is simple. Pull the rods out slowly, and if the multiplication factor exceeds 1, the chain reaction becomes self-sustaining. Push the rods back in, and you shut it down. On December 2nd, 1942, everything is ready. The pile contains about 50 tons of uranium and uranium oxide embedded in roughly 400 tons of graphite. It's an ungainly structure, roughly 25 feet across, built by hand by a team that includes not just physicists, but also high school students and laborers who have no idea what they're building. Fermi gives the order to withdraw the control rods, one step at a time. He's watching the neutron counters, doing calculations on his slide rule. Because this is 1942, and that's what you have. And at 3:25 in the afternoon, the counters begin to climb in that unmistakable exponential curve. The multiplication factor crosses 1. The reaction is self-sustaining. Fermi lets it run for about 28 minutes, carefully monitoring the power level, then orders the control rods reinserted. The reaction stops. Arthur Compton, who oversees the project from Chicago, makes a famous coded phone call to James Conant at Harvard. The Italian navigator has just landed in the New World. Conant asks, "And how did he find the natives?" Compton replies, "Very friendly." It's a moment of quiet triumph, celebrated with a bottle of Chianti that someone had stashed away for the occasion. But there's no time to linger on celebrations, because the achievement of Chicago Pile 1 is not an end. It's a beginning. It proves that a self-sustaining chain reaction is possible, which means plutonium production is possible, which means one of the two paths to a bomb is now open. But scaling up from a pile that produces half a watt of power to reactors that can breed kilograms of plutonium is an engineering challenge of an entirely different order. And simultaneously, the isotope separation effort, the other path, the uranium path, is ramping up to industrial scale in a place that most Americans have never heard of, a rural valley in eastern Tennessee, that the Army is about to transform into one of the most secret cities in America. They called it Oak Ridge. Now, to understand what happened at Oak Ridge, you have to appreciate just how absurd the problem of isotope separation really is. We talked about this earlier. Uranium-235 and uranium-238 are chemically identical. They're both uranium. They react the same way with acids. They form the same compounds. They dissolve in the same solutions. The only difference between them is that U-238 has 3 extra neutrons in its nucleus, which makes it about 1% heavier. That's it. And you need to separate them, not just a little bit, but almost completely. Natural uranium is only about 0.7% U-235. For a bomb, you need it enriched to around 80% or higher. Weapons grade is typically above 90%. So you're trying to take this incredibly rare isotope and concentrate it by a factor of more than 100, and your only handle on the problem is a tiny difference in mass. It's like trying to sort identical-looking marbles by weight, when the heavy ones are only 1% heavier than the light ones. And for every marble you want, there are 139 you don't. The Manhattan Project pursued multiple separation methods simultaneously because nobody knew which one would actually work at scale. This was a deliberate strategy driven by General Leslie Groves, the Army engineer who took over management of the entire bomb project in September 1942. And Groves is a fascinating figure. He's the anti-Fermi in many ways. Where Fermi is quiet, precise, and understated, Groves is blunt, aggressive, and supremely confident. He's a large man, heavy-set, with a reputation for being difficult to work with. He'd just finished overseeing the construction of the Pentagon, which at the time was the largest office building in the world, and he was hoping for an overseas combat command. Instead, he got told he was going to run this secret weapons project. He wasn't happy about it. But Groves had a gift that turned out to be exactly what the project needed. He could make decisions fast, he could manage enormous construction efforts, and he was utterly ruthless about cutting through bureaucracy. When scientists wanted to study a problem for another 6 months, Groves would say, "We don't have 6 months. Pick a direction and go." So Groves looked at the isotope separation problem and said, essentially, "We'll try everything." 3 main approaches were pursued at Oak Ridge. The first was electromagnetic separation, championed by Ernest Lawrence at Berkeley. Lawrence, you might remember, is the man who invented the cyclotron, the particle accelerator that had become the workhorse of nuclear physics. His idea for isotope separation was conceptually simple, almost elegant. You ionize uranium atoms, strip off some electrons so they carry an electric charge, then shoot them through a strong magnetic field. Charged particles curve in a magnetic field, and the radius of that curve depends on the particle's mass. Heavier U-238 ions curve on a slightly wider arc than lighter U-235 ions. So at the end of their flight path, they land in slightly different spots, and you collect them in separate bins. It's basically a giant mass spectrometer, scaled up to industrial size. Lawrence called his machines Calutrons, California University cyclotrons. And here's where the engineering gets wild. Each Calutron needed enormous magnets to create the magnetic field, and those magnets needed massive amounts of copper for their windings. But copper was a critical war material in 1943. It was needed for shell casings, wiring, everything. There wasn't enough to spare. So someone, and accounts vary on exactly who suggested it first, proposed using silver instead. Silver is actually a better electrical conductor than copper. The problem, of course, is that silver is enormously expensive, but the U.S. Treasury had plenty of it sitting in vaults. So the Manhattan Project borrowed, literally borrowed, about 14,700 tons of silver from the Treasury Department. Nearly 15,000 tons. The Treasury officials were apparently horrified at the idea, and there's a possibly apocryphal but widely repeated story about a Treasury official correcting a Manhattan Project colonel. In the Treasury, we don't speak of tons of silver. Our unit is the troy ounce. Every ounce was meticulously tracked, and after the war, it was all returned. The Calutrons were built in huge oval buildings called racetracks, because that's what the arrangement looked like from above. Rows of these massive units arranged in an oval. The first set, called alpha racetracks, did a rough initial separation. The output from those went into beta racetracks for further enrichment. Thousands of workers operated these machines, many of them young women. They were called Calutron girls, who sat at control panels monitoring dials and adjusting knobs. Most of them had no idea what they were making. They were told to keep certain readings within certain ranges, and that was it. The secrecy was extraordinary. You could live and work in Oak Ridge and have absolutely no idea that you were helping to build an atomic bomb. But here's the thing about the Calutrons. They were painfully slow. Each machine could only process tiny amounts of uranium at a time. The separation factor per pass wasn't great, and the throughput was limited. Lawrence had promised much better performance than the Calutrons actually delivered, and there were constant problems. The vacuum systems leaked. The ion beams were unstable. The collectors would get contaminated. It was a brute force approach, and it worked. but it was never going to be efficient enough on its own. The second method was gaseous diffusion. And this one is beautiful in its logic, even if it was nightmarish in its engineering. The idea goes back to basic physics, Graham's law of effusion, from the 1840s. If you have a gas made up of molecules of different weights and you force it through a barrier with incredibly tiny pores, the lighter molecules will pass through slightly faster than the heavier ones. So you convert uranium into a gas, uranium hexafluoride, UF6, which is the only practical uranium compound that's gaseous at reasonable temperatures, and you push it through a porous barrier. The gas that comes through is very, very slightly enriched in U-235. How slightly? Each stage increases the concentration by a factor of about 1.0043. That's less than 0.5% improvement per stage. Think about what that means. To go from 0.7% U-235 to weapons-grade material, you need thousands of stages arranged in a cascade. The output of one stage feeds into the input of the next. The Oak Ridge gaseous diffusion plant, called K25, required over 2,000 stages. The building itself was U-shaped, and when it was completed, it was the largest building in the world under one roof, 1/2 mile long on each side of the U. Over 40 acres of floor space. And every stage needed pumps, pipes, valves, and those porous barriers, all of which had to handle uranium hexafluoride, which is one of the most corrosive substances you can imagine. It reacts with moisture, it attacks most metals, it destroys conventional lubricants and gaskets. Every seal, every pump, every barrier material had to be specially developed. The barriers themselves were perhaps the single hardest engineering challenge. You need a material with pores small enough to allow molecular effusion. We're talking about holes on the order of millionths of an inch. And the material has to withstand corrosion from UF6. And it has to be manufactured in enormous quantities with consistent quality. Multiple approaches were tried. Nickel powder barriers, sintered nickel mesh, various composite materials. The development was plagued with problems. And for a long time, it wasn't clear that a suitable barrier could be produced at all. The Kellex Corporation, a subsidiary of the engineering firm M.W. Kellogg, was brought in to design and build K25, and their engineers had to essentially invent new fields of chemical engineering on the fly. The third method was thermal diffusion, which was actually the simplest in concept. You create a temperature gradient, a hot surface next to a cold surface with a gas between them, and the lighter isotope tends to migrate toward the hot side, while the heavier isotope drifts toward the cold side. The Navy had been secretly working on this under a physicist named Philip Abelson at the Philadelphia Navy Yard. Groves initially hadn't been interested in thermal diffusion because it was the least efficient of the three methods. But in 1944, when it became clear that the gaseous diffusion plant was behind schedule, Groves ordered a thermal diffusion plant, called S50, built at Oak Ridge in a matter of months, right next to the K25 building, using steam from K25's power plant as its heat source. S50 could do a rough initial enrichment, bumping the U-235 concentration up from 0.7% to maybe 2%. Not much, but it meant the gaseous diffusion cascade didn't have to do as much work on the front end. And this is where Groves's pragmatic genius really shows. He chained the methods together. Thermal diffusion did the first rough cut. Gaseous diffusion took it further. Then the calutrons did the final enrichment to weapons grade. Each method compensated for the weaknesses of the others. It was redundant, expensive, and consumed staggering amounts of electricity. Oak Ridge used more electrical power than New York City at its peak. But it worked. By the summer of 1945, Enough highly enriched uranium had been produced for one bomb. Just one. That's how hard this was. Years of effort, billions of dollars, tens of thousands of workers, 3 separate industrial-scale processes running simultaneously, and the output was enough fissile material for a single weapon. Meanwhile, the plutonium path was advancing on its own parallel track, and the scale of that effort was, if anything, even more staggering. Because while Oak Ridge was wrestling with isotope separation, another secret city was rising in the desert of eastern Washington state, along the Columbia River, in a place called Hanford. And the challenge at Hanford was different, but equally daunting. They needed to build full-scale nuclear reactors, not the careful experimental pile that Fermi had assembled under a squash court, but massive production reactors capable of irradiating tons of uranium and breeding significant quantities of plutonium. The engineering firm DuPont was brought in to design and build them, and the story of how DuPont's conservative, methodical engineering culture clashed with, and ultimately saved, the physicists' ambitious designs is one of the great untold dramas of the entire project. Because the physicists nearly made a mistake that would have doomed the entire plutonium production effort, and it was DuPont's stubbornness. The kind of stubbornness that comes from decades of building chemical plants where a single miscalculation can kill hundreds of people. That caught it. Here's what happened. When the physicists designed the production reactor for Hanford, they calculated how many uranium fuel slugs would be needed, how many process tubes would hold those slugs, and how much cooling water from the Columbia River would have to flow through the reactor to carry away the enormous heat generated by a sustained chain reaction. They came up with a design that called for around 1,500 process tubes. It was elegant, efficient, and based on the best physics available. DuPont's engineers looked at it and said, essentially, we want more tubes, a lot more. They pushed for a design with around 2,004 tubes. The physicists were annoyed. More tubes meant more complexity, more expense, more weight, more everything. Why over-engineer something when the calculations said 1,500 would work? But DuPont had a philosophy, drilled into them by decades of working with explosives and toxic chemicals at their plants along the Brandywine River in Delaware and elsewhere. Their philosophy was simple. You don't know what you don't know. You build in margin, generous margin. Because in a chemical plant, the things that kill you are the things you didn't anticipate. And nuclear reactors were so new, so unprecedented, that the list of things nobody had anticipated was almost certainly very long. So DuPont insisted on the extra tubes, and because Groves respected DuPont's engineering judgment, and because he'd hired them precisely for this kind of disciplined conservatism, the extra tubes went in. And thank God they did. Because when the B reactor at Hanford, the world's first full-scale plutonium production reactor, went critical for the first time on September 26, 1944, something completely unexpected happened. The reactor started up beautifully. Power levels climbed. Everything looked perfect. And then, after several hours, the power began to drop. Slowly at first, then faster. The reactor was poisoning itself, and nobody had predicted it. What was happening was a phenomenon called xenon poisoning. When uranium fissions inside a reactor, it produces a whole zoo of fission products, radioactive fragments of the split atom. One of those products is iodine-135, which is mildly annoying but not a huge problem. The issue is that iodine-135 decays, with a half-life of about 6.5 hours, into xenon-135, and xenon-135 turned out to be one of the most voracious neutron absorbers ever discovered. Its cross-section for capturing thermal neutrons is almost absurdly large, about 2.6 million barns, if that number means anything to you. For comparison, most materials have cross-sections measured in single digits or tens of barns. Xenon-135 was a neutron sponge on a scale nobody had imagined. So as the reactor ran, it built up iodine-135, which decayed into xenon-135, which started gobbling up the neutrons that were supposed to be sustaining the chain reaction. The reactor choked on its own waste products. Power dropped to zero. The reactor shut itself down. And the physicists stood there, initially baffled. Now, Enrico Fermi and the brilliant Canadian physicist John Wheeler figured out what was happening fairly quickly. Wheeler had actually done some theoretical work on fission product poisoning before this, and he suspected xenon almost immediately. But figuring out the cause and fixing the problem were two different things. The fix was straightforward in principle. You needed more reactivity, more neutrons. Enough excess neutron production to overwhelm the xenon absorption and keep the chain reaction going despite the poison. And how do you get more reactivity? You load more uranium fuel into the reactor, which means you need more process tubes. And this is where DuPont's conservatism saved the entire program. Because those extra 500 tubes that the physicists had argued against, they were already built into the reactor. They were sitting there, empty, waiting. All the engineers had to do was load additional uranium fuel slugs into those spare tubes, and suddenly the reactor had enough excess reactivity to power through the xenon poisoning. Within a few days, the B reactor was running at full power, breeding plutonium as intended. If DuPont had listened to the physicists and built only 1,500 tubes, the reactor would have been a very expensive paperweight. They would have had to shut it down, redesign it, rebuild it. A process that would have taken many months, possibly pushing the plutonium bomb past the end of the war. Think about that for a second. A corporate culture of over-engineering, born from a century of manufacturing dynamite and gunpowder, may have altered the timeline of the Second World War. The Hanford site itself was enormous. 3 production reactors were eventually built, B, D, and F, spaced miles apart along the Columbia River so that an accident at one wouldn't affect the others. The cooling water pumped from the Columbia flowed through the reactor at tremendous rates, carrying away heat from the chain reaction, and then was held in retention basins before being returned to the river. The irradiated uranium fuel slugs, after spending weeks inside the reactor absorbing neutrons and breeding plutonium, were pushed out the back of the reactor into deep cooling pools, where they sat for weeks more, while the most intensely radioactive, short-lived fission products decayed. Then they were transported to massive chemical separation plants, the so-called canyon buildings, T plant and B plant, where the plutonium was chemically extracted from the uranium and fission products. These canyon buildings were genuinely remarkable pieces of engineering. They were essentially enormous concrete boxes, 800 feet long, 65 feet wide, with walls several feet thick to shield workers from the lethal radiation of the dissolved fuel. All the chemical processing was done remotely, using periscopes and mechanical manipulators, because the solutions being handled were so radioactive that a few seconds of direct exposure would be fatal. The separation process itself was based on a method called bismuth phosphate precipitation, developed by Glenn Seaborg's team It exploited the fact that plutonium, in certain chemical oxidation states, would co-precipitate with bismuth phosphate, while uranium and most fission products stayed in solution. By cycling the plutonium through multiple precipitation steps, changing its oxidation state back and forth, they could progressively purify it until they had plutonium nitrate pure enough for weapons use. The quantities involved were tiny compared to the throughput. Tons and tons of irradiated uranium went in, and what came out, after all that processing, was grams of plutonium at a time. Eventually kilograms. But the whole operation, the reactors, the cooling ponds, the canyon buildings, the chemical processing, was designed to run continuously, around the clock, producing plutonium as fast as nuclear physics would allow. And while all of this was happening at Hanford and Oak Ridge, there was a third secret city, the most famous one, perched on a mesa in the mountains of northern New Mexico, Los Alamos. This was where the actual bombs were being designed, and the story of Los Alamos is really the story of one man's extraordinary ability to manage genius. That man was J. Robert Oppenheimer. Oppenheimer is one of the most fascinating figures of the 20th century, and he's worth spending a little time with. Born in 1904 in New York City to a wealthy family, his father was a successful textile importer. Oppenheimer was the kind of prodigy that makes other smart people feel inadequate. He entered Harvard and graduated summa cum laude in 3 years. He studied at Cambridge, then at Göttingen in Germany, where he earned his doctorate under Max Born, one of the founders of quantum mechanics. He spoke 6 languages. He read the Bhagavad Gita in the original Sanskrit for pleasure. He wrote poetry. He was thin, intense, chain-smoked, and had a charisma that people described as almost magnetic. When Oppenheimer was in a room, everyone was aware of it. But here's the thing about Oppenheimer that made him the right choice for Los Alamos. And it wasn't his physics, although his physics was very good. It was his ability to understand what other people were thinking. He could sit in a room with 20 brilliant, egotistical scientists, each one convinced their approach was right, and somehow synthesize their ideas, mediate their disputes, and keep them all moving in the same direction. He was, by all accounts, a spectacular manager of intellectual talent. Groves recognized this almost immediately when they met in October 1942. And it was Groves who selected Oppenheimer to lead the weapons laboratory, over the objections of security officials who were deeply uncomfortable with Oppenheimer's pre-war associations with Communist Party members and sympathizers. Groves didn't care. Or rather, he cared, but he cared more about getting the bomb built. He later said that Oppenheimer was a genius, and that genius was essential, and that he would take responsibility for the security risk. It was one of the most consequential personnel decisions of the war. Los Alamos was established in early 1943 on the site of a boys' ranch school that Oppenheimer had known from his youth. He'd spent time in New Mexico recovering from illness as a young man and had fallen in love with the landscape. The mesa sat at about 7,300 feet elevation, surrounded by ponderosa pines and dramatic canyons, with views of the Sangre de Cristo Mountains. It was isolated, defensible, and beautiful. And into this remote setting poured some of the greatest scientific minds of the century. Hans Bethe, who had figured out how stars generate energy. Edward Teller, the Hungarian physicist already obsessed with the possibility of a hydrogen bomb. Seth Nettermeyer, who would pioneer the implosion concept. George Kistiakowsky, the explosives expert. Rudolf Peierls and Otto Frisch, whose memorandum had started the whole military effort. John von Neumann, arguably the greatest mathematician alive, who would solve the critical problem of shaped explosive lenses, and dozens more: chemists, metallurgists, ordnance specialists, electronics engineers. The central problem they faced was this: you have fissile material, either uranium-235 or plutonium-239, and you need to assemble a supercritical mass fast enough to get a significant nuclear explosion before the thing blows itself apart. Because here's the challenge that isn't immediately obvious. As soon as a chain reaction starts in a supercritical assembly, energy begins releasing at an exponential rate. The material heats up, expands, and that expansion reduces the density, which reduces the reactivity, which tends to shut the reaction down. So you're in a race. You need the chain reaction to proceed through as many generations as possible, each generation doubling the energy, before the expansion disassembles the core and stops the reaction. If the core comes apart too early, you get a fizzle. A small explosion, maybe equivalent to a few tons of TNT, but not the city-destroying blast you're after. For uranium-235, the solution turned out to be relatively straightforward, at least in concept. You take two subcritical pieces of uranium-235 and slam them together very fast using a gun-type assembly. Essentially, you fire one piece down a cannon barrel into the other piece. When they meet, the combined mass is supercritical, the chain reaction starts. And because uranium-235 has a relatively low rate of spontaneous fission, meaning it doesn't emit many stray neutrons on its own, you have enough time during the assembly process to get the pieces together before a premature chain reaction starts. This design was called Little Boy, and the scientists were so confident it would work that they never even tested it before dropping it on Hiroshima. They built one bomb, shipped it to the Pacific, and used it. No prototype, no test shot, nothing. That's how certain they were about the physics. But plutonium was a completely different story, and this is where the entire project nearly came undone. See, the plutonium being produced at Hanford wasn't pure plutonium-239. When uranium-238 absorbs a neutron in a reactor, it becomes plutonium-239, that's true. But some of that freshly made plutonium-239, sitting there in the reactor while the chain reaction continues around it, absorbs another neutron. And when plutonium-239 absorbs a neutron without fissioning, it becomes plutonium-240. This was a problem that Emilio Segre and his group at Los Alamos discovered in the spring of 1944, and it was devastating. Plutonium-240 has an extraordinarily high rate of spontaneous fission, vastly higher than uranium-235 or even plutonium-239 itself. It's constantly spitting out neutrons, all on its own, no chain reaction needed. And you can't easily separate plutonium-240 from plutonium-239 the way you can separate uranium isotopes, because they're only one mass unit apart and they're the same element, so they have identical chemistry. The Hanford plutonium was contaminated with enough plutonium-240 that a gun-type assembly simply would not work. The stray neutrons from the plutonium-240 would initiate a chain reaction while the two pieces were still coming together in the gun barrel before full supercriticality was achieved, and you'd get a fizzle. The pieces just couldn't move fast enough. You'd need a muzzle velocity that no gun could produce. This realization hit Los Alamos like a thunderbolt. They had been counting on gun-type assembly for both bombs. Suddenly, the plutonium path, the path that Hanford's massive reactors were churning away to support, looked like it might be a dead end. Months of work, billions of dollars in 1944 money, 3 enormous reactors, those canyon-sized separation plants, all of it potentially for nothing, unless implosion could be made to work. Now, implosion had been floating around as an idea for a while. Seth Nettermeyer, a quiet, somewhat solitary physicist, had been advocating for it since 1943. The concept is this. Instead of slamming 2 pieces together like a gun, you take a single sphere of plutonium that's subcritical at normal density, and you compress it. You squeeze it uniformly from all directions, crushing it inward, increasing its density. And here's the beautiful physics. A denser sphere of fissile material has a lower critical mass. The neutrons don't have to travel as far to find another nucleus to split. So if you compress the plutonium enough, fast enough, it crosses the threshold into supercriticality, not by adding more material, but by making the existing material denser. And because the compression happens so fast, we're talking microseconds, the assembly time is incredibly short. Much shorter than a gun barrel. So even with all those stray neutrons from plutonium-240, you can get to supercriticality before a premature chain reaction ruins everything. That's the concept. Beautiful in theory. Nightmarishly difficult in practice. The problem is symmetry. You need the compression to be perfectly uniform, squeezing equally from every direction simultaneously. If the implosion is even slightly lopsided, the plutonium core squirts out sideways, like squeezing a wet bar of soap. Instead of compressing to supercritical density, it deforms, and the whole thing fails. Think about that for a second. You need to take a sphere of metal roughly the size of a grapefruit and crush it uniformly inward using high explosives, and the shock wave converging on that sphere needs to be spherically symmetric to within a fraction of a millimeter, with conventional explosives. That's the engineering challenge. Nettermeyer's early experiments were discouraging. He was wrapping cylindrical metal tubes with explosives and trying to compress them symmetrically, and the results were messy, crumpled, asymmetric, nothing like the uniform compression needed. Oppenheimer brought in George Kistiakowsky, a Ukrainian-born chemist who was one of the world's foremost experts on explosives, and Kistiakowsky essentially took over the implosion program. The relationship between Kistiakowsky and Nettermeyer was not a happy one. Nettermeyer felt sidelined from his own idea, but the stakes were too high for diplomacy. And then there was von Neumann. John von Neumann had been thinking about shaped charges and the behavior of converging shock waves, and he proposed the idea of explosive lenses. Here's the analogy. Think about how an optical lens works. Light travels at different speeds through glass and through air, and by shaping the glass correctly, you can take a flat wave of light and bend it into a converging wave that focuses to a point. Von Neumann realized you could do the same thing with detonation waves. If you used 2 different explosives, one fast-burning and one slow-burning, arranged in carefully calculated shapes, you could take the diverging detonation wave from a single detonation point and reshape it into a converging, spherically symmetric wave. Each lens would take a chunk of outward-moving detonation and redirect it inward. And if you tiled the surface of a sphere with enough of these lenses, all detonated simultaneously, the converging waves would merge into a single, beautifully uniform implosion front. This was the breakthrough. But turning it into reality required solving problems that had never been attempted before. The shapes of the lenses had to be computed with extreme precision, and this was 1944. No electronic computers were available yet, so the calculations were done by hand, by teams of human computers. many of them women, working with mechanical calculators. The explosive compositions had to be developed and tested. Kistiakowsky's group cast thousands of explosive lens assemblies, testing them with increasingly sophisticated diagnostics. They used a technique where they'd embed thin metal foils in the explosive and use flash X-ray photography to capture the shape of the converging shockwave at the instant of detonation. Each test told them whether the wave was smooth or lumpy, and they'd adjust the lens geometry and try again. The final design used 32 explosive lens segments fitted together like a soccer ball, 20 hexagonal and 12 pentagonal, surrounding an assembly called the pit. The pit itself was a thing of considerable ingenuity. At its center was the plutonium core, a sphere about the size of a large orange, roughly 3.5 inches in diameter, weighing about 6 kilograms. It was actually made in 2 hemispheres, and it was warm to the touch because of the radioactive decay. Surrounding the plutonium was a natural uranium tamper, a heavy shell that served 2 purposes. First, its inertia helped hold the assembly together for a few extra fractions of a microsecond as the chain reaction progressed, giving the reaction more time to build before the whole thing flew apart. And second, the uranium could reflect neutrons back into the plutonium core, improving the efficiency. At the very center of the plutonium sphere was a small cavity, and inside that cavity sat the initiator, a component called the urchin, designed by James Tuck. The urchin was a small sphere of beryllium and polonium, arranged so that when the implosion wave crushed it, the polonium's alpha particles would strike the beryllium and produce a burst of neutrons at precisely the right moment to kickstart the chain reaction. Timing was everything. The neutrons had to appear at the instant of maximum compression, not a microsecond before, not a microsecond after. By the spring of 1945, the implosion design was coming together, but confidence was nowhere near what it was for Little Boy. There were too many things that could go wrong: the lens geometry, the simultaneity of the detonators, the behavior of the plutonium under compression, the initiator timing. Oppenheimer and Groves agreed. This design had to be tested, and so we come to Trinity. The test site was in the Jornada del Muerto, the Journey of the Dead Man, a stretch of desert in southern New Mexico, about 200 miles south of Los Alamos. They chose it because it was flat, remote, and already within a military bombing range. The device, which they simply called the gadget, was assembled in a ranch house nearby and then hoisted to the top of a 100-foot steel tower. It looked nothing like a weapon you could drop from an airplane. It was a 5-foot diameter sphere of cables, detonators, and bolted explosive segments, ugly and industrial, like something from a mad scientist's workshop. The test was scheduled for July 16, 1945. In the days leading up to it, tension at the site was almost unbearable. Some of the scientists organized a betting pool on the yield. Oppenheimer guessed around 300 tons of TNT equivalent. Teller optimistically wagered 45,000 tons. Kistiakowsky bet a month's salary against $10 from Oppenheimer that the device would work at all. Enrico Fermi, in his characteristically deadpan way, was taking side bets on whether the bomb would ignite the atmosphere, a possibility that had been studied and theoretically ruled out, but which still haunted some of them in the small hours of the night. The weather was bad. Thunderstorms rolled through the desert, and the test was delayed from its original 4 a.m. time. Rain and lightning near a device surrounded by high explosives and radioactive material. Nobody was comfortable with that. Groves was furious about the delay. The Potsdam Conference, where Truman would meet Stalin and Churchill, was about to begin, and Groves knew the president wanted to know whether this thing worked before he sat down at that table. At 5:29 a.m., the storm had passed enough. The countdown reached 0, and the firing circuit closed, sending simultaneous electrical pulses to 32 detonators arranged around the sphere. The explosive lenses fired. The converging detonation wave raced inward at about 8,000 meters per second, compressing the plutonium core from a density of roughly 15.5 grams per cubic centimeter to perhaps twice that. The Urchin initiator released its burst of neutrons, and in the span of about 1 microsecond, 1/1,000,000th of a second, the chain reaction proceeded through roughly 80 generations of fission, each one doubling the energy of the last. The energy released was equivalent to about 21,000 tons of TNT. The fireball was blinding. Observers at base camp 10 miles away felt the heat on their faces like opening an oven door. The light was visible in 3 states. The mushroom cloud rose to over 38,000 feet. The 100-foot steel tower simply ceased to exist. It was vaporized. The desert sand beneath it was fused into a glassy, mildly radioactive substance they would later call trinitite, a pale green glass that you can still find fragments of today. Oppenheimer would later say that in that moment, a line from the Bhagavad Gita came to mind. "Now I am become death, the destroyer of worlds." Kistiakowsky, covered in dust, turned to Oppenheimer and said something like, "I am sure that at the end of the world, in the last millisecond of the Earth's existence, the last human will see what we saw." Kenneth Bainbridge, the test director, was more blunt. He shook Oppenheimer's hand and said, "Now we are all sons of bitches." Word reached Truman at Potsdam in a coded message. "Operated on this morning. Diagnosis not yet complete, but results seem satisfactory and already exceed expectations." A later, more detailed report described the yield, the fireball, the shockwave, and Groves's assessment that the weapon was ready for combat use. Truman's demeanor at the conference reportedly changed overnight. He became more assertive, more confident in negotiations with Stalin. He had the bomb, and he knew it worked. What happened next unfolded with a speed that still feels breathtaking when you lay it out on a timeline. Trinity was July 16th. The components of Little Boy, the uranium gun-type bomb, were already en route to Tinian Island in the Pacific, carried partly by the cruiser USS Indianapolis, which delivered the uranium projectile and target assembly on July 26th, and was then sunk by a Japanese submarine 4 days later in one of the worst naval disasters in American history. The plutonium core for the second bomb, Fat Man, the implosion design, a near twin of the Trinity device, was shipped separately by air, arriving on Tinian on August 1st. And now you had both weapons on a tiny coral island in the middle of the Pacific, less than 1,500 miles from Japan, and the question that had been theoretical for 3 years became the most consequential decision of the 20th century. What do you do with them? There's a tendency, looking back, to imagine this as a single dramatic moment, a president sitting alone in a room, weighing the fate of cities. But it wasn't really like that. The decision to use the bombs emerged from a cascade of smaller decisions, committee recommendations, military planning assumptions, and a kind of institutional momentum that had been building since 1942. The Target Committee had already met multiple times, starting in the spring of 1945. They'd drawn up lists of Japanese cities, evaluating them based on military significance, population density, psychological impact, and, this is a detail that catches people off guard, whether they'd been left relatively undamaged by conventional bombing so the effects of the atomic weapon could be clearly assessed. That was an explicit criterion. They wanted a clean demonstration of what the bomb could do. Hiroshima was near the top of the list from early on. It was a major military headquarters, home to the Second Army, an embarkation port, and it had industrial areas. But it also had a large civilian population, roughly 350,000 people at the time. Kyoto was originally on the list too, and it was actually Secretary of War Henry Stimson who personally removed it. Stimson had visited Kyoto, knew it as Japan's ancient cultural capital, and argued that destroying it would generate lasting bitterness that would poison post-war relations. Groves pushed back more than once, but Stimson held firm, so Kyoto was spared, and Nagasaki eventually moved up the list as an alternate target. Now, there were voices arguing against using the bomb on cities. Some of the scientists who'd built it, the people who understood better than anyone what it would do, circulated petitions and wrote reports urging alternatives. The Frank Report, authored by a committee of Chicago scientists led by James Frank in June 1945, recommended a demonstration shot. Detonate the bomb on an uninhabited island or desert, invite Japanese observers, show them the power, and give them a chance to surrender before using it on a populated area. It was a reasonable idea on paper, and it reflected genuine moral anguish. But the military planners and the interim committee, chaired by Stimson, rejected it for several practical reasons. What if the demonstration failed? You'd have revealed your hand and wasted one of only 2 bombs. What if the Japanese weren't impressed, or dismissed it as a trick? And there was the prisoner of war concern. If you announced a demonstration in advance, the Japanese might move Allied prisoners to the target site. Leo Szilard, the same man who'd originally pushed Einstein to write that letter to Roosevelt, circulated his own petition urging Truman not to use the weapon without first offering Japan a chance to surrender under specific terms. The petition gathered about 70 signatures at the Met Lab in Chicago, but Groves made sure it moved slowly through channels. It didn't reach the president's desk before the bombs were dropped, so the order went forward. On July 25, 1945, the directive was issued by General Thomas Handy, acting on behalf of the Joint Chiefs. It authorized the 509th Composite Group, commanded by Colonel Paul Tibbets, to deliver the first atomic bomb after about August 3, 1945, on one of 4 targets: Hiroshima, Kokura, Niigata, or Nagasaki. The phrasing of the order is worth noting. It didn't require further presidential approval for each individual bomb. It authorized the use of additional bombs as they became available. The machinery was in motion. August 6, 1945, a Monday. The B-29 Enola Gay, named after Tibbets's mother, took off from Tinian at about 2:45 in the morning. Tibbets was at the controls. The crew was 12 men. Little Boy sat in the bomb bay, 9,800 pounds, 10 feet long, 28 inches in diameter, looking like an oversized trash can with fins. Navy Captain William Parsons, the weaponeer, actually completed the final assembly of the bomb in flight, inserting the cordite charges into the gun mechanism after takeoff. He did this because he'd watched 4 B-29s crash on the Tinian runway the night before, and he was terrified that a crash on takeoff with a fully armed nuclear weapon could destroy half the island. The flight to Hiroshima took about 6 hours. The weather was clear. At 8:15 local time, the bomb bay doors opened, and Little Boy fell for 43 seconds, detonating at about 1,900 feet above the city, almost directly over Shima Surgical Clinic. The yield was approximately 15 kilotons, less than Trinity actually, but devastating beyond anything the world had seen in warfare. The fireball reached temperatures hotter than the surface of the sun. Everything within a mile of ground zero was essentially annihilated. The blast wave radiated outward at the speed of sound, collapsing buildings, shattering glass miles away. Then came the thermal pulse, intense heat that ignited fires across the city, fires that merged into a firestorm. And then the radiation, both the initial burst and the lingering fallout. The numbers are hard to hold in your mind. Somewhere between 70,000 and 80,000 people were killed essentially instantly, within seconds or minutes of the detonation. By the end of 1945, the death toll had climbed to perhaps 140,000 as people succumbed to burns, injuries, and radiation sickness. Many of the dead were civilians, women, children, elderly people, Korean forced laborers. The survivors, who would come to be called hibakusha, carried injuries and radiation effects for the rest of their lives. Some of them are still alive today, still telling their stories. Truman announced the bombing in a public statement, describing Hiroshima as a military base and warning Japan that if they did not surrender, they could expect a rain of ruin from the air, the like of which has never been seen on this earth. Behind the scenes, the administration waited for a Japanese response. It didn't come immediately. The Japanese government was divided. The military hardliners wanted to fight on, believing they could inflict enough casualties during an invasion to negotiate better terms. The peace faction, led by Foreign Minister Shigenori Togo and backed quietly by Emperor Hirohito, wanted to accept the Potsdam Declaration's terms, but the word unconditionally was a sticking point because it was ambiguous about the emperor's fate. And so, 3 days later, August 9th, the second bomb was dropped. Fat Man, the implosion device, the plutonium bomb. The primary target that morning was actually Kokura, not Nagasaki. Major Charles Sweeney piloted the B-29 boxcar, and when they arrived over Kokura, the city was obscured by clouds and smoke drifting from a firebombing raid on nearby Yahata the day before. The bombardier couldn't get a visual fix. The orders required visual bombing, not radar. And after 3 passes over the city, with fuel running low and Japanese anti-aircraft fire starting to find their altitude, Sweeney diverted to the secondary target. Nagasaki. Even there, clouds covered the city. It was only in the last moments before the bomb run that a brief gap in the clouds revealed the Mitsubishi industrial complex in the Urakami Valley, and the bombardier released Fat Man at 11:02 in the morning. The bomb detonated about 1,600 feet above the valley, with a yield of roughly 21 kilotons, more powerful than Little Boy actually. But the hilly terrain of Nagasaki channeled and contained the blast somewhat, so the destruction, while catastrophic, was less total than Hiroshima's. Approximately 40,000 people were killed immediately, with the toll eventually reaching around 70,000 by the end of the year. Here's the thing that haunts historians. The timing of Japan's surrender is tangled up with another event that happened on August 9th, the same day as Nagasaki. The Soviet Union declared war on Japan and launched a massive invasion of Manchuria. For the Japanese leadership, especially the military faction, the Soviet entry may have been as shocking as the bombs themselves, because it destroyed their last diplomatic hope. They'd been trying to use the Soviets as intermediaries to negotiate peace terms. Now that door was slammed shut. So when Japan finally surrendered on August 15th, with Hirohito's recorded radio address, the first time most Japanese citizens had ever heard their emperor's voice, it's genuinely difficult to untangle how much of that decision was driven by the atomic bombs, how much by the Soviet invasion, and how much by the cumulative weight of years of conventional bombing, naval blockade, and military collapse. Scholars have debated this for 80 years, and honest ones will tell you it was probably all of these things, woven together. The war ended, and then the world had to figure out what to do with the knowledge that couldn't be unlearned. The scientists scattered. Some returned to universities, eager to leave Los Alamos behind. Others stayed, drawn into the accelerating arms race. Oppenheimer became the most famous scientist in America, appointed chairman of the General Advisory Committee of the new Atomic Energy Commission. He argued against developing the hydrogen bomb, a weapon hundreds or thousands of times more powerful than the fission bombs, on both technical and moral grounds. Edward Teller pushed for it relentlessly. When Truman authorized the hydrogen bomb program in January 1950, the rift between Oppenheimer and Teller became permanent. And then, in 1954, Oppenheimer's security clearance was revoked after a grueling hearing in which his past associations, his ambivalence about the hydrogen bomb, and his complicated personality were used against him. Teller testified against him. It was, by many accounts, a political crucifixion, a man punished not for disloyalty, but for having a conscience that made powerful people uncomfortable. Oppenheimer retreated to Princeton, where he directed the Institute for Advanced Study until his death from throat cancer in 1967. He was 62. The arms race, meanwhile, became the defining feature of the Cold War. The Soviets tested their first atomic bomb in August 1949, years earlier than most American officials expected, aided significantly by espionage. Klaus Fuchs, a physicist who'd worked at Los Alamos, had been passing detailed bomb designs to Soviet intelligence. The Americans tested the first thermonuclear device, Ivy Mike, in November 1952, a 65-ton apparatus that vaporized an entire island in the Eniwetok Atoll and yielded over 10 megatons. The Soviets followed with their own thermonuclear weapons. By the mid-1960s, both sides had enough nuclear warheads to destroy civilization several times over. The doctrine of mutually assured destruction, MAD, and the acronym was not accidental, became the strange, terrifying logic that kept the peace. You don't attack me because I'll destroy you. I don't attack you because you'll destroy me. And so we both sit here, fingers near the button, forever. There were close calls, more than most people realize. The Cuban Missile Crisis in October 1962 is the famous one. But there were others. False alarms from early warning systems, communication breakdowns, moments when a single officer's judgment call may have prevented launch. In 1983, a Soviet lieutenant colonel named Stanislav Petrov received satellite warnings that 5 American intercontinental ballistic missiles had been launched toward the Soviet Union. Protocol demanded he report it up the chain, which would likely have triggered a retaliatory strike. Petrov judged it was a false alarm. The system was new. 5 missiles seemed too few for a first strike, and he was right. A satellite had misinterpreted sunlight reflecting off clouds. One man's skepticism may have saved millions of lives. Think about that for a second. The entire architecture of nuclear deterrence, with its thousands of warheads and billions of dollars, came down to one person's gut feeling on a night shift. And that's the world the Manhattan Project built. Not just the bombs themselves, but the entire framework of nuclear anxiety, arms control treaties, non-proliferation efforts, and the quiet, constant vigilance that has kept these weapons from being used in war since Nagasaki. The technology also gave us nuclear power, reactors that generate electricity without burning fossil fuels, descended directly from Fermi's Chicago pile. It gave us nuclear medicine, isotopes used every day in hospitals to diagnose and treat cancer. It reshaped geopolitics, redrew alliances, and created institutions: the International Atomic Energy Agency, the Nuclear Non-Proliferation Treaty, designed to manage a genie that could never be put back in the bottle. If you've stayed with me this far, or even if you've been drifting in and out, here's what I keep coming back to. The story of the atomic bomb is, at its heart, a story about what happens when human curiosity, pure, beautiful, unstoppable curiosity about how the universe works, collides with human conflict. Röntgen didn't set out to build a weapon when he noticed that strange glow on his workbench. Becquerel wasn't thinking about warfare when he left uranium salts on a photographic plate. The Curies, Rutherford, Bohr, Fermi, Hahn, Meitner, they were chasing understanding. They wanted to know what matter was made of, how atoms held together, what happened when you broke them apart. And the answers they found were so powerful, so fundamental, that the world was never the same. The people who built the bomb knew this. Many of them carried that weight for the rest of their lives. Some found peace with it, believing they'd shortened the war and saved lives that would have been lost in an invasion. Others never stopped questioning. Isidore Rabi, who'd watched the Trinity test, said years later that the physicists had known sin, and that this was a knowledge they could not lose. It's a heavy thought, but it's also a deeply human one. The recognition that knowledge and responsibility are inseparable, that understanding the world means accepting what that understanding makes possible. So as you lie there, maybe feeling the heaviness of sleep starting to settle in, think about this. Every piece of technology around you, every light, every signal, every material in the walls and wires of wherever you are right now exists because someone, somewhere, was curious enough to ask how something worked. And the answers to those questions always carry consequences. Some wonderful, some terrible, most somewhere in between. The story of the atom is the most dramatic version of that truth, but it's the same truth that runs through all of engineering, all of science, all of human making. We figure things out. We build things. And then we have to live with what we've built and decide, together, what to do next. That's the work that never ends. And it's worth doing. Even now. Especially now. Rest well.